Okay, thanks. I hope people online can help me very well. So today I will talk about access the initial condition with multi-particle correlation, which is a common tool for heavy ion physics. And I will show how can we use such information from initial condition to proper nuclear structure in heavy ion physics. So basically, this is a very simple cartoon which illustrates the evolution of little band heavy ion collisions at high energy. When you smash two heavy ion, the lead, at near the speed of light, you can create a very hot and dense matter, the quark plasma. And then quickly after the formation, the quarks and gluons will form hadrons, which interact with each other until the freeze out condition, and they leave the system. If you put a beautiful detector there, you can catch all the information. And by doing some data analysis and based on comparison to theoretical models, we try to extract the information about the quark plasma. That is basically the key goal of heavy ion physics program at years. And then I noticed this is the only talk which is about ALICE. So I want to emphasize that ALICE is actually the largest and also the dedicated heavy ion experiments at the ELHC. I think it's fair to say it's the largest heavy ion experiments in the world. And actually last year we worked so hard to get this ALICE report or yellow paper or white paper out, which is a summary of the 10 years journey through the TCD studies. So basically the idea is we really want to do some experimental studies and make the comparison to theoretical models and see if we can study the quark plasma. But as already shown here in this picture, there's a big unknown for the initial conditions, which in fact brings a big uncertainty of the overall study for the quark plasma. So here I borrowed one of the famous slides from Julian, which show you the initial entropy distribution from different models. Those are popular initial state models, which have been commonly used by Bayesian analysis, etc. And just quickly judged by eye, you can realize all the distributions are very different. Yes. So how can we access such information on the initial condition in experiment? Our common tool is the anisotropic flow. The concept of flow has been widely used in also lower energy physics nuclear structure studies. And for high energy heavy ion collisions or non-central heavy ion collisions, when the two heavy ions match with each other, the overlap region between the two colliding nucleons show you like this American football show. And this initial state spatial anisotropy will be converted to the final state anisotropic particle expansion, quantified by the anisotropic flow coefficient. So in the final state, we want to look at elliptic shape or triangular shape and use all these flow coefficients to quantify the properties of the quark plasma. Well, now let me repeat. The flow is defined as the azimuthal angle of the produced particle with respect to a common symmetry plane. The definition is very clear. However, the side end, the flow symmetry plane, is unknown in experiment. You cannot construct it event by event. So what we can do is we use a particle azimuthal angle correlation. For example, two particle correlation. We have a correlation between any pair phi1, phi2, and we can do a simple math, and then in the end, you can get some information of Vn squared. That means even you don't get the mean value of the Vn even by event, you can calculate the RMS value of the Vn distribution based on a two particle correlation without knowing the flow symmetry plan event by event. This is of course only the concept. This is what we hope to have. While in reality, what we actually get is a flow with two particle correlations, so Vn squared plus some additional contamination called non-flow effects, which includes some resonance decay or jets. For example, if there's a particle like phi-meson decay into K plus K minus, when you use this K plus K minus to look at the correlation between the two, you will have a big bias in such correlations, which bring you the information about the mother particle, the phi-meson, instead of anything connected to the initial geometry or quark plasma. So this is something we want to remove or suppress in experimentation. So normally, the non-flow contamination in two particle correlation can be scaled with 1 over n. N is the number of particles that produce in final state. And to suppress this effect, one of the very smart ideas is using multi-particle correlation or generate multi-particle correlation. For example, we can construct a 4-particle cumulus. When you have the correlation between 4 particles, you have the total 4-particle correlation. But then you can also subtract all the lower order correlation, for example, between phi1, phi3, phi2, phi4, or phi 1, phi 4, or phi 2, phi 3. So you subtract all the low order correlations, and what remains is the genuine correlations among 4 particles altogether. And with a quick estimation, you can see the non-flow effect of the 4 particle cumulants is actually the order of 1 over n to the cube, which is much smaller than the non-flow condensation in 2 particle correlation. Using a very similar idea, you can construct 2, 4, 6, even 8 order cumulants, 8 particle cumulants, which will largely suppress the non-flow effect. And yesterday it has been discussed that the 2 and multi-particle correlation has different sensitivity to flow fluctuation. And what we know is to the leading order, there's a positive contribution in Vn2 and negative contribution in Vn4, 6, and 8. I will go to the details later when we should discuss it with us. So here is one example. The left-hand side show you the first Vn measurement at LHC-1-2 program. The lead collision at 5.02 TeV. The red points are the V2 basically the shape. Measure with 2 particle correlations. And in order to suppress the non-flow coming from resonant decay, etc., we apply the eta separation. So that there's a delta eta separation between the 2 particles to make sure we can suppress most of the non-flow effects. And then just judge by this comparison, you can see the data can be very nicely described by hydrodynamic model calculations or predictions. Actually, this is also from you and from analysts, I believe. And also Jackie is involved in this paper. And while in the right-hand side, we basically repeat a very similar comparison in xenon conditions right after we have the xenon data. And you can also see very good agreement between the data and the hydrodynamic model prediction. So based on that, we can claim that the quark group plasma that we create at the LHC still behave like the perfect fluid. That is very.
The agreement for xenon very central and very peripheral.
Those are simple predictions, and also for this EKRT calculation, that's a small problem because they haven't considered energy formation. That's exactly the point. But I will go to the next slide.
I've got a basic question. So, can I measure V2 with 3 particle correlations?
No, because if you look at this formula, because you want to construct anything with 5 respect to the psi n. So if you do a 2 particle or with even order, you have a minus psi, have a plus psi, so you don't have anything left over. And then in the end, you will only have Vn. So simple, if you have 3 particle correlation, you have psi, minus psi, you have a plus psi, you have something left. And then you have to use the information about flow symmetry plan to know.
So another way of saying it is that every collision has a random orientation. So you can only measure rotation in variant quantities.
Okay.
So you have to add up different particles, and all the ends have to add to 0.
So is it only the even number of particle correlations that are
not necessarily.
If you want other things like a 3 particle correlation involving V2, it has to be a mixed harmonic correlation. So you could have a V1 and V2 correlator, like 1, 1 minus 2, with any integers that add up to 0. But if you want only 2, then that has to be even numbers so that they can cancel.
Okay.
That makes sense.
Indeed, we can make a 3 particle correlation, but the n will be different. So for example, we can do 2 phi 1 plus 2 phi 2 minus 4 phi 4, which will give you a correlation between psi 2 and psi 4, different symmetry plan correlation.
Yeah. Okay.
Which is part of the study that I'm going to talk about.
Okay.
Are there any assumptions in this 1 over m cubed non-flow effect? You would expect that if you have like 100 particles, but there 10 particles in a correlated like a jet, that you would actually get a bigger effect even for.
This is my concept. This very early estimation from I think Raymond, etc.
There must be some assumption there, right?
Yeah, it's just you have something that correlates some small number of particles, any number, like creates clusters or something. But as you create more and more of those clusters, it's just combinatorics that when you do this 4 particle correlation, it's all possible ways of selecting 4 particles. So just the combinatoric scales this way if you add more correlated clusters where the clusters are not correlated with each other.
Okay, we have to digest them.
But again, this is just a very rough estimation. And if you, for example, if you have hydrogen, which is a on-color model doesn't have flow, you run it, you will see it might not satisfy with 1 over m.
Right.
But you will say whether hydrogen is precise enough to estimate no flow. We do not know. Yeah, so indeed, there are some disagreement between the model and data shown in the right-hand side, and that's because in that calculation, there's no consideration of any nuclear structure. So we also have a different comparison later on, and when we do the zoom in into the central collision for 100% here, you can see the open circle is a lead collision data, the V2, and then the solid red point is the xenon V2. You can see there's a much larger V2 in xenon collisions, and if you do the ratio, you cancel out to some extent the dependence on the kinematics and also dependence on the evolution of the plasma. And then what you can see is you can directly come up with model calculations with different beta 2 deformation. And then you can find the one with a very large beta 2 equal 0.18 for xenon. You can describe the data so much better than the one without deformation.
When you do the ratio, the number of nucleons are much different though. So how do you do that ratio?
No, we just use the sense centrality. Just assume that for the sense centrality determination of percentile, it has the same shape but different size.
Okay.
Because I guess it's fair to assume that for xenon collision at 5.44 and lead at 5.02, the QGB evolution will be very similar.
Okay, and so this percentage centrality, this is in terms of particle multiplicity, right? It's sort of percentage close to the maximum number of particles you can produce. How is that defined?
So basically, in Alice, we have multiple ways to do the centrality determination, and for this measurement, we are using multiplicity in the forward and backward direction. So we look at the uncharged distribution, and then we do the global fit to extract the centrality.
Okay.
The medium effect won't be cancelled because the same centrality and size are different. The geometry is the same.
Well, whether it's cancelled completely, I don't know. But for this comparison, this is a really apple to apple.
Yeah, that's right. That's full hydro.
Full hydro calculation. And then you will say whether we can directly compare these V2 calculation, the ratio between V2 to the ratio of eccentricities. That is the
Question.
Yes.
So in informed nucleus, can you distinguish whether it's an odd or even system? So here it's 129 genomes, so there's one unpaired nucleon here. Does one see this? If you had, I don't know, 130 or 128, would that be different?
Only if the shape changes.
Yeah, we can describe, we can figure out between that.
Well, I guess are these all stable?
I'm sure you can get a stable even xenoisotope.
But we don't have many options. So this is more like accidental data taken that we get.
I thought the rate is more precise.
So this is not something which developed for heavy ion physics, but we will take that data. We took the data anyway, and turns out to be quite interesting.
Well, I think in this Alice plot, we don't even see the uncertainty, right? I mean,
That's not. This is not Alice plot. That's Juliano's plot.
Yeah.
But his styles, you don't even have uncertainty.
The left is Alice, they have our error bars, they're pretty small.
But yeah, indeed, if you look at
it's
this
like
one.
2%. But precisely, you might actually see.
But right now we are making the new plots with also very precise measurements. And if you have any calculation, I'm happy to throw them together. I will code your net data.
The thing that you can basically see by eye is the red curve on the left shoots up faster than it should if they were both the same shape. So you can really kind of by eye see that xenon 129 must have a quadrupole deformation to increase these V2 fluctuations like that in central collisions.
Maybe you see one neutron and you change the beta 2 by 1%. Okay, that's pushing.
Yeah, no, yeah, we only see it if the somehow the shape in some sense or the n-body correlations change in some appreciable way.
But I can also share the story that we did when we discussed the results. Right? We see the dramatic increase, and then the first idea come to our mind. Slightly younger generation is so it's a smaller system, so the fluctuation must be larger, and you would expect larger flow from them. But then we also have very senior people who did the low energy measurements before, and they immediately realized it's nuclear structure. So that's why I guess this is one of the first studies in the field in high energy avionics physics that we started at the ELC. We realized it's important to check the nuclear structure and also have the right calculations in the initial state. And but then, so we have the measurements of V22, V24, V26, V28. So why we are bothering with all these complicated measurements? The idea is we can, with different multi-particle cumulants, we can construct different moments. And by the moments, the mean, the arm, the variance, the skewness and kurtosis, we can reconstruct the online PDF probability density function, which basically show you how does the Vn flatted done by that. And then we can also use a very useful assumption that if Vn is proportional to eccentricity, then the normalized PV2 distribution will be almost identical to the P eccentricity distribution. And then if you have the data, you can directly compare to the model in the initial state calculations. This has been validated with this calculation. So the difference between the initial state eccentricity calculation shown by this dashed line is very similar to the final state hydrodynamic model calculations.
So why do you need the assumption that Vn is proportional to En? Because that's not the reality.
Because this is not strictly valid if you go to a slightly more commercial application. So if you think about centrality 40 to 50 and above, it's not valid anymore. So in your hydro calculation, you can look at Vn as function of eccentricity, look at the spread, it's getting wider and wider. And there will be a cubic response in the large eccentricity, which Jackie has proved at the first work.
I've got a question. So this in the upper right-hand corner, that's from calculations, right? The distribution for V2.
These are calculations, also with Atlas data point, black points,
okay.
and also the black shadows are Alice main.
I see. Gotcha.
What's wrong with the data you go up and down?
Which data?
The Alice data.
Black ones there.
The black is the data. The rest is model calculation. So there's a statistical fluctuation.
Oh.
Yeah. So these black shadows are Alice calculate. Alice measurements based on the moment.
Okay.
These measure some coefficients of some parameterization, such as smooth curve, right? At least doesn't measure directly.
No, so those two measurements are done differently. So this is based on the unfolding based on the liquid power function using this moment. While Atlas is basing unfolding procedure.
Why the points are not smooth?
Model calculations,
No, the points. At least,
there's no point here, right?
Those are the
It's
models,
only
right?
the black line, black shadows.
yeah, but
It's very
there are
no. This is not edit points. So
oh,
those are colorful shadows.
Those are all models, it's just statistical.
It's a checkerboard.
And I guess what is also calculation from Trim's proof of IP class not possible. Early calculation. So you see, it's quite useful to have a position calculation.
How constraining is this? I wonder, like, do you need to make assumptions on the actual distribution to say like those moments are sufficiently constraining to say something? It's always tricky to reconstruct the distribution for the moments, right?
And for this is I think Atlas was using Gaussian fluctuations. Well, this is based on the electric power function, which they're showing. But then in the end, I guess it's more or less what we expect, because when you use such information and you start to predict the moments or the cumulants, they are very precise.
But the point is you don't assume something Gaussian, otherwise you don't need over higher moments, right? You want to see deviations from the Gaussian.
Yeah, that's basically what we did. So if you do a calculation of the ratio between V26 divided by V24, the Gaussian distribution tells you it should be identical. The ratio should be 1, while we see 2% of deviation, which tells you it's not a Gaussian fluctuation. But this is not most exciting part. That so having is a lead collision. Lead is not so exciting for our discussion for nuclear structure. But the question is, well, when we have the distribution, right, we also try to see how can we construct an initial state model. And basically, if we put all the calculation together from initial state, the difference is not so large. So it's not easy to see which model was slightly better than the other, even for the simple calculation of lead. But then question is, we also have the very precise measurements of V2, 2, 4, 6, and 8 in xenon conditions. And we should repeat the same work and get it down for the PV2 distribution in xenon. And then we would expect, or we hope to have the calculation either from initial state or from final state hydrodynamic model calculations with different nuclear structure. And it should be quite simple to have an implementation of beta 2 for different 18 or 20 with some triaxial structure of them. And we can see if there's any impact in the final PV2 distribution. For example, you already see that recent results, the nuclear deformation for them, the V2 will be different. So the mean V2 will be different. And the whole trend, let's say the whole distribution will shift toward the larger V2 if you have deformation.
So you already have calculation for V2 for V2 duration, which in the bottom panel.
Yeah.
Which describe the data. But that has information of those. Different, oh yeah.
I think this is the initial state calculation for VUSB hydro. So we should have the beta 2 from 18.
Oh, they're both from the same paper. Okay.
It's from the same.
Yes, they have
So
the- yeah,
initial-
they have the deformation, yes.
So you also ask about the linear response, right? You can see the calculation. So basically, when you assume there's a perfect linear response between V and 2 eccentricity, you would expect the V24 divided by V22 will be identical to epsilon 24, right? Epsilon 22. And they are not identical. So this is the simple VM measurement or VM with fluctuations, while our real picture is more complicated because of event by event fluctuation in the Newton distribution, which gave you not only V2 but also higher harmonic V3, V4. And previously we discussed how does a VM, V2, especially V2, fluctuate event by event. But we have more. Like how does a precise flow symmetry plan fluctuate event by event or in different kinematic region? And how does how do the VN and different flow coefficient correlate with each other? And how do the flow symmetry plan correlate with each other? And whether this information will tell us anything about initial conditions or the nuclear structure. So one simple idea is about the flow decorrelation, or also named flow symmetry plan decorrelation. The idea is for the initial condition, you have the so-called Parkinson plan, which is determined by the Newton distribution of overlap region. But then if you look at final state, the precise might depend on the kinematic region, PT or eta. And this has been confirmed in at least by a recent paper from my students. But you can see a more than 5 sigma effect of deviation from unity, which confirmed flow symmetry plan fluctuating in different PT regions.
Can you go through all these different axes so I have a better understanding? 5.2, 5.3, 5.4, and all these.
So when you have a V2, if you have a elliptic shape, right? You have a long axis, so you can define the side 2 along this. And then for V3, this is the psi 3, and V4 is the psi.
Okay, but can you go to the next slide? Okay, you're just drawing them.
This is just it's based on this cartoon to illustrate the psi 2, 3, 4 in different PT range.
Gotcha.
Will be different.
Okay.
And this is confirmed. So I'm not going to talk about why we are using it, but the new idea is it was submitted like last month. When you do a very similar calculation for the decorrelation, you realize the decorrelation effect, the size of the decorrelation really depends on the shape. So here is a calculation for uranium at the rig. And then when you put a different deformation, so basically represented by the colors, you will see a hugely different. And this difference is so large, it's much larger than the uncertainty that we have for data. So if you just simply put them together, you can easily constrain the model. And in the solid and dashed lines, there are different calculations for one is called the flow plan correlation, decorrelation. The other is flow magnitude decorrelation. The physics is very similar. So this is basically the flow symmetry plan correlation that we can use. And the other is look at the correlation between different flow coefficients. So when we look at the V2, V3, V4, there's a certain correlation between them. When you look at the V2 and V4 correlation is positive everywhere. This means if you have a large V2 in an event, then you will also get a very large V4 in the event. But then when you do the normalized symmetric cumulants, the interesting part will be seen here. So this is hydrodynamic calculation using EKRT initial condition, but with very different eta values, with fixed eta values or with different parameterized eta values at some temperature. And when you do the normalized magic equivalent, they all fall into one line. But it doesn't matter how does QGP evolve, the results are identical. And why it is? Actually, we come back to the so-called linear response between the flow coefficient. V2 is proportional to epsilon 2, V3 is proportional to epsilon 3. And then you can write down this formula. Because you have a linear response, you would expect this final state normalized magic equivalent, the V2, V3 correlation will be the same as initial state epsilon 2, epsilon 3 correlation. And this has been validated also in different initial state model and with different intervals. It's basically very similar. So in that sense, we know normalized magic equivalence is insensitive to the intervals, even if we made everything in the final state after the expansion of the problem process. And it all bring you the information about initial conditions and give you the direct access into the correlation between epsilon 2 and epsilon 3.
Why is epsilon 2, 4 so sensitive?
Because for V4, you have a very large nonlinear response coming from a V2 or epsilon 2. So when you consider V2 and V4 correlations, you are also considering V2 correlation with V2.
I didn't quite catch, where does the nonlinear response come from?
So when you have a hydrodynamic evolution, when you start to build V4, the V4 has two contributions. One is from the geometry epsilon 4, this shape. The other is from epsilon 2 squared. So the V2 shape also contributes to the V4.
Because V2 squared gives something, okay.
So
V2 squared rotates the same as before, so they can both contribute, but since V2 is large, V2 squared actually can be competitive. Normally you think of this as sort of this power series expansion, but the second harmonic can be large compared to the other ones, so sometimes higher powers, V2 can contribute.
I see.
we also have the measurements at the LHC, and we can find that for the nonlinear, so the V2 contribution in V4 is a dominant, is actually larger than epsilon 4 contribution in centrality of 20%. So this basically gives us a direct access into the initial condition, and then at around 2 at 5 TeV, also we repeat the same measurements, which is much more precise. And most of the models can, to some extent, describe the shape, or for some centrality, they can even catch the data. But yesterday, I also talked to Wilke about the MSC V42, which is a V2 V4 correlation. I think most of them still failed or cannot catch the data. But the interesting part I want to emphasize is in the right-hand side. So now, if you do the calculation with epsilon 2, epsilon 3 correlation in the initial state, previously we see if you have a PV2 distribution, there's no big difference between them. But now you can see the results are very different for NSC 3-2, which means when you look at the correlation between epsilon 2 and epsilon 3, they are different by even a factor of 3 between JESSCAPE and IP glass.
So this is correlations event by event?
Event by
It's a correlator, but
And do all these models describe the V2 and V3?
yes. So they all describe V2, V3, even in PT, but they cannot describe the correlation between V2 and V3. So I can predict, even when we don't have the final state calculation, we can predict this IP glass now will overestimate the data by quite a bit. Overestimate the magnitude by quite a bit.
So how do we know which one is closer to reality?
Oh, this is data.
Oh, okay.
Those are black points. The uncertainty is almost negligible. So if you put them together, you can see here in centrality, let's say 40 to 50%. This is what 0.15.
Oh, power. Why don't we just watch that? Oh, maybe just not sure why that full screen.
Better, so
Yeah, maybe it overheated or something.
Yes, it's hot and dense matter.
No, this is not just on the screen.
Yeah.
Oh,
We just see if we have a problem with power in the room.
it's in the office. There's also just a button.
It's overheating.
But there must be some reason it turned off.
I
It's-
don't think it was normally just a shut off. It's too hot. Try to cool it, so.
Oh, is it that?
I just push the button. No, it doesn't.
No.
Maybe.
Okay, that's not good.
Yeah. Not good. It suddenly just
Oh, I
turned
see.
itself off.
What about the connection with the laptop?
It's good.
It's still good. So
Okay.
we just have a problem with the projector here for those people on Zoom that don't know what we're doing.
Yeah. Yeah,
Uh,
I know. It's just like I had a workshop a month ago, and I know that the connection with the laptop actually. So
Laptop is good, and we can proceed.
Yep. We're good now. Let's get
okay, cool.
So this is one of the simplest measurements that we can do for correlation between flow coefficient. It's actually the V2 square V3 square correlation based on symmetric movement. And but then you will ask, what is the general correlation between any order of flow coefficient to whatever orders? That needs a very complicated multi-particle correlation. But then before we move to the more complicated calculation, I want to show you how can we use normalized symmetric movement to probe nuclear structure. Those are two independent studies, both based on a BD model, different system, uranium on the left-hand side. So here you can see the set 1 is basically beta 2, 0, beta 4, 0, beta, and then set 2 start to add beta 2, and then beta set 3 at a larger beta. But then if you look at the results in the central collision 0 to 10, 0 to 20%, there's quite some differences between the calculation. So if you start to put the beta 2 and beta 4 inside, you start to see a big anti-correlation between V2 and V3. A very similar result in the right-hand side, but now I'm talking about the correlation between V2 and V4, which is positive everywhere. But then if you, it's a very messy plot. But if you look at the ratio between beta 2 equals 0 to beta 2 equals 0.18, the blue point, you will see a significant decrease in trend, which tells you there's a much larger correlations in the deformed nuclei if you compare to the calculation without a deformation of them. So basically, the results are confirming each other for the uranium collision at the rig or xenon collision at the LHC. And for such a big differences, it's very easy to probe using the xenon data.
So you're saying that the beta 4 enhanced the correlation from V2 and V4, but
No, it's not beta 4, it's beta 2, right? So if you compare the theta 2 and theta 3, it's a fixed beta 4. But then when you change the beta 2, it's changed the correlation between V2 and V3.
and the second plot was also beta 2 versus.
And here there's no beta 4. Okay. So we didn't change beta 4 at all. Only changed the beta 2 from 0 to 0.18. But then we also changed the triaxial structure. So we have gamma equals 0 and equals 27 degrees, which is more precise, it gets more close to the reality. There's basically no difference. So the greenish points with a very large uncertainty are compatible with 1.
So what does these results tell us?
So I guess it means for the correlation between V2 and V4, it is sensitive to the deformation of them or the deformation in general. And if you have a larger deformation, you have a larger correlation between V2 and V4 and also V2 and V3. However, the triaxial structure does not affect significantly for this correlation.
So with the different hydro calculations give similar results, or
Yes.
would it?
Yes, there was for some of the hydro calculation, I guess there are some available calculation for isobar, but the uncertainty are very large. I saw the previous calculation from Hui Chao and Hao Jie. I don't know where go. Someone else also have a prediction. But this should be easy to check. This is also one of the simple calculation they usually do.
It seems. You don't want to show data on the spot, or is data?
There is no data right now, but I can promise that we will have the data available during initial study. Because I already know.
Well, the for cumulative is there, right? Or no, this is for Xenon.
This is Xenon.
But okay, the problematic region is from 30% onwards.
Yes. So for if you remember the flow results, right? It was simple V2 measurement. the difference start to see, I guess, in central 0 to 10%, maybe even 0 to 5%. You have a precise calculation. And here for some of these complicated global like normalized symmetric cumulants, you might see a deviation around 15 or 20%, which extends your central region. And then we can also use high order correlations, whatever VN to more different moments. And some years ago, I guess almost nine years ago, Zhang Yong started to list some of the ideas, but he put many thoughts, but he doesn't want to calculate it. And many people try to derive it by hand, manually. But what we do is we have a generic algorithm for whatever multi-particle cumulants or multi-particle correlation. You can copy paste this C code, then run it, and you get all the terms that you need. So one example is now we can extend the correlation between Vn and Vn from a second order, which is called symmetric cumulants, to the high order correlation. For example, I can use 6-particle cumulants to measure the correlation between V2 to the power 4, V3 square, or V2 power 2, V2 square, V3 power 4, or even the first measurements of the correlation between the 3 harmonics, V2, V3, and V4. And then you can also do some more similar for 8-particle cumulants. Everything can be done with previous code. And then here I show you the measurements done by Alice. Well, there are many points, but what we see is for correlation with 4-particle, it's negative. But if you go to 6-particle for these, and these, it's all positive. And then when you go back to the 8-particle, it's all negative again. So it's a 4-particle, 6-particle, 8-particle with a sign of minus, plus, and minus have been observed in lab calculations. And then what does it mean? And then we also did some model calculation with hydrodynamics, by divisional with ABD initial conditions. And we can find, again, if we are using the assumption Vn is proportional to epsilon n, or V2, V3, are proportional to epsilon 2 and epsilon 3. We do a calculation in the final state with hydrodynamic involution. We also have the calculation in initial state, epsilon 2, epsilon 3 to the higher order. They are basically identical. So that means we can use the mixed harmonic cumulants to constrain the high order correlation in the initial stage, which cannot be accessed with only low order symmetric cumulants. And then the question is, can we also perform such measurements with 6-particle cumulants in xenon-xenon condition?
Okay, so this V24 didn't work, right? This epsilon and the Vn, but for all of these it works. That's the statement.
What do you mean V24?
For the symmetric cumulative 2,4.
No, sorry, I forgot to explain. So those points are not Alice data points. Those are hydrodynamic calculation.
Right.
The lines, the shadows are the initial state calculation. So here there's no data comparison. Data model comparison is all model.
Because you just showed that the symmetric cumulative between V2 and V4 doesn't work, the initial state predictor. But then the statement is for these ones it works.
This is V2, V3.
Yeah, V2, V4 it doesn't work, but here, firstly, I
The
don't.
only one where the initial state predictor doesn't work is V2, V4.
No, V2, V3 will work, and V2, V4 will not work because of the nonlinear response.
These ones.
This is V2, V3. So I changed the order from 2nd to the 4th or to the 6th. Still works for V2.
And for all V2, V3 combination works,
V2,
and for all V2, V4 doesn't.
So if you don't involve the higher order, then it's okay. And then I had to admit we only have 1 million events in there from Alice, and it's impossible to perform such a man. And then I heard some rumor that if you want to probe the triaxial structure, you need 3-particle or 6-particle. And here are 6-particle correlations. So what if Atlas can or CMS can do a very similar analysis like that and see what we can? You have roughly 30 million events. So,
Use your code.
yeah, I mean, it's public. So. And then I move on to the correlation between different symmetry planes, right? So we also discussed whether we have to use 2-particle or 4-particle. In fact, here is a 5-particle correlation. You can do V2, V3 here, but then you have something left over, which is psi2, psi3 correlation. So, and then you can use such a measurement to probe any correlation between the flow symmetry plane. And you can see for these points, the black points, they are consistent with 0. And we know this is not 0, this is not 0. It only means there's no correlation between psi2 and psi3 in heavy ion pollution. That's early measurements done by 12 years ago. But then in the right-hand side, we have the almost position measurements at the around 2 the collision. And here you have the correlation between psi2 and psi4, which increase. And that is basically the cosine 4 psi4 minus 4 psi2. And what does it mean? In central collision, centrality 0 to 10%, the rho is very small. The cosine is very small, which means the psi2 and psi4 are almost uncorrelated because the overlap region is -4. So the psi2 and psi4 are not aligned with each other. And if you go to more peripheral, you have this American proportion. Then the psi2, the psi2 will start to align with the psi4, and you start to see a very strong correlation, which is very close to 1. And using a very similar idea, yes.
The 7223, the CMS measurement, there are hydro calculations for that, and they are not anywhere close to the measured data. You didn't get the calculations for 7223.
No, this is 3 years ago. And when we prepared the paper, it was 4 years ago. We don't have any position calculation.
The last one, the 7223.
It depends on which model you are talking about. For example, here, if you look at the Trento calculation, those are Bayesian analysis, due to Trento. They cannot fit the Alice data. And then how can we use the correlation between psi to talk about nuclear structure? And here I just pick up one simple example, the correlation between psi2 and psi4. The idea is also very simple. So if Zeno in central collision there's no deformation, then it will be a round ball, like with a round ball. And then we will say there's no alignment between psi2 and psi4. And the correlation of rho 422 should be close to 0. And that is basically the result that you can see for beta 2 equals 0. The results are very small. But then if you start to add the deformation, you're from 18. It immediately enhances the correlation between psi2 and psi4. Because in the initial condition, in central collision, instead of a round, you start to give the shape. If you consider some combination of body or body interactions. And then this is also very significant. There's a deviation from centrality below 10%. And if you do a central collision measurements, you can already see something like 40% deviation. But this is AMPG simulation, and we are going to present the Alice data in a few months from now.
And gamma there refers to a triaxial angle, basically.
Yeah. Okay. So here it was not marked clearly. This is beta 2 equal 0.18, but with a triaxial.
I see.
And this is beta 2 equal 0.18, but with a oblate, as a gamma equal 0.
Prolate is prolate, but it's axial symmetry. The other one has no axial symmetry. Okay.
So the triaxiality doesn't matter.
No. So it's actually not a surprise because is it?
Why not? It's a 3. You said you need 3-particle
No,
correlation.
no,
This is a 3-particle
exactly.
correlation.
That's why we want to check this absorber to see whether there's an effect. But then you can see with the current uncertainty is more or less jumping around 1. But when they start to say 3-particle correlation, it might not be true for every 3-particle correlation. I think Gemini's or Julian's argument is more about PT correlation. You need to pick up 3 PT correlation. But then all previous discussion are based on the anisotropic flow related to what we call the shape. And we also have a size which quantified by mean dt or radial flow. So if you have a small size, you have a large mean dt. If you have a large size, you have a small mean dt. So how can we use such information? And there are several papers on this. I just pick up 2 examples. There are of course many others which I haven't listed here. So you can use the skewness or intensive skewness, basically 3-particle PT correlation. PT correlation with some normalization. And you can also do some kind of cumulants if you want to follow a very similar idea like azimuthal angle correlations. You construct higher order cumulants, you subtract the lower order correlations. And then to make everyone happy, we also try to derive automatically with some generic algorithm. So we can extend to whatever higher order correlation you want. And here we actually derived it up to 10, I think, with some weights. So in principle, we can do such amendments at the LHC. And I just show you two examples. One is from AAPD calculations, again with different nuclear structure. But right now the uncertainty is very large because we have like a million events in total for million bytes. But we do have the Alice measurements already public for the Alice preliminary results. So here is a 3-particle PD-PD correlation in different system LED in red, the xenon in blue, and even PP collisions here. And I think it will be very nice to have also some model calculations with a different nuclear structure for them. Because if we believe, or if they argue is correct, that with a 3-particle correlation in PD correlation, we can probe the triaxial structure, then this data will tell us something. And the uncertainty is very large.
If you just go back to one more slide before. So there's the difference was the Y scale is very fine, yeah. But that is still around 10% difference is observable.
So it depends on the order, right? So this mean PT, that's basically the first order, and then second order, and 3, 4, 5, 6. The uncertainty is getting larger and larger. Sometimes we don't even trust the uncertainty. This is purely from the bootstrap.
Also, so this is data that you show here, not simulation.
No, this is simulation. Okay. This is simulation. We did it in purpose with only 1 million events. Because in Alice data, we only have 1 million events.
I see.
But just try to give you some prediction. In Alice, we are not able to have any prediction memory for it. And that's why I want to bring it up to this medium so that Atlas or CMS can do this PT correlation.
How many events do you have?
Okay, so there was not much difference between xenon and LED, right, on the data for this.
There's no, so you are talking about the next
Right,
one.
right.
Yeah.
There's no difference between LED and xenon, right?
Mhm.
Why do you say the triaxiality should be clear from this plot? If
No,
LED is
This is what we knew from previous papers. From some, which I guess Zhou is online. Can you help me? No. I remember both Zhou and Juliano have their independent checks for these 3-particle correlation. And they show some signal for the triaxial structure with the PT correlation.
So how to understand this centrality dependence, going down and up to the 3-particle.
Well, actually, I don't know. So I got this result had been approved by Alice for quite a while, and in that conversation, there's no any discussion about nuclear structure. And then I realized this is the old result, and okay, can we use it?
So the most central points, how central are they? How to
Should be 0 to for that should be 0 to 5%.
the last point only 0 to 5.
But you see the in charges in DND is very close to 2,000, 3,000.
Okay.
I think Shanif has something about his ultracentral defluctuation.
Yeah. But this is lead. Right, so we are talking about the dramatic increase in lead. Was then
Xenon, there's nothing to see, right?
so I guess for at least for this calculation, right now we are using hygiene, which then also implement with any nuclear structure. So standard algorithm without a nuclear structure, and it will be very nice to have some predictions with a serious consideration for nuclear structure.
Why did you choose hygiene 50 as a comparative?
This one with my work.
Oh,
But I guess this is because in Alice we have a large hydrogen production. And also, I guess in one of the previous papers, so which present here, yeah, hydrogen more or less shows you the right trend for mean PT and mean PT fluctuation. But if you symbol A in PT, the transform model, the mean PT itself is completely wrong. So any prediction made by the AMPT is not really bad. So while we do this AMPT just to show how large uncertainty we might get. But then we go back to the Bayesian analysis. So right now we are using the information from VM and MPT. Not only just simple VM element, but also VM with 2 or 4 particle cumulants, which means you consider flow fluctuation. And then similarly for MPT, can use mean PT of pi kp or with delta PT, which is considering the PT fluctuations in the Bayesian analysis. We try to extract both a QGP evolution and also the initial condition. The result is showing in the very beginning of the slides, but if you think about the energy profile, they are not the same. And then there are more. So for this the scalar Bayesian analysis, they start to include higher harmonics up to V8 or V9, and also they have nonlinear response, chi and k, and normalized symmetric cumulant, etc. And they also start to try to study what is the sensitivity of each observable to different parameters in the Bayesian analysis. I think also in this paper, Wilke and collaborator also did quite some work for the inclusion of PID flow and PID spectrum. But my personal comment is more done always means good, and especially in the scalar Bayesian analysis, they are using several correlated observables. And so when you use the data to constrain the model, you need to make sure they are independent, or you have a careful considerations in your Bayesian analysis. As far as I know, it is not the case in the current calculation. So sometimes you start to put more, you put A, you put B, you put A plus B, A minus A divided by B, but then doesn't means independent information.
So just maybe to look at these observables are correlated. How the Bayesian analysis will show that.
In principle, it should.
Yeah.
If you do piece theory part, it's like very small number.
Yeah, I mean, I think there's not really a problem in the principal component analysis. See that immediately. But of course, there's always a theoretical and an experimental uncertainty matrix. So it depends a little bit what's the dominant uncertainty. For many of these very differential flow measurements, the emulation certainly will be dominant. But then you can properly do these correlations because we know the principal components. Experimentally is very difficult. So we don't know, for instance, like the spectra and the mean PT, they're obviously correlated. Okay, experimentally we don't know how exactly, so that's not taken into account. Experimentally, what we do is we have some simple, like if nearby PT bins, they're correlated, the sum assumed, nearby centrality bins are assumed correlated. Okay.
So here, when you say correlated, are you saying correlated in systematic uncertainty, correlated in the parameters of the model, like physics?
No, so in principle, those are very similar names. Think about the chi whatever compared to the rho. Those are basically the same observable, just with normalization by Vn to some power. But then you use Vn, you use chi, and you use rho. Basically, use a similar information twice.
Okay,
Same information physically or same information experimentally? What are we saying?
In the Bayesian analysis, benefit data.
But then I don't know, if you look at all the wiggles out there for some of these bins, I mean, this correlation is not the worst of the problems. And I think, yeah, we thought a little bit about it, like we fit the spectra, but we also fit the yield and the mean PT, and they're obviously the mean PT is the average of the spectrum. And also the mean PT is supposed to be a little bit more accurate because integrated, so there's a bit less sensitivity. So we decided for that reason to keep it.
But for example, you might also have some issue with if you do PT differential flow, and if you also have the mean PT, you basically can integrate flow of Vn.
Right.
And you use Vn also.
Yeah, so in principle, yeah. So, but these integrated ones are a little bit more reliable in some ways. So that's why we keep both of them. But the correlation are also included, so I don't think there's necessarily a problem.
So the question is, how do we deal with the not independent information we get from data? From data analysis?
What's for instance very difficult to deal with, nobody really deals with, is that the 2.76 and 5.02 are somewhat trivially correlated. They're usually assumed to be independent.
But then I move to the last part about the VPT-VN correlation. So we talk about the shape, we talk about size separately. This is already there have been a big discussion already in this program, INT program for the VNPT correlation, the role program. The idea is also very simple. That we want to see, I mean, we assume that the Vn is proportional to epsilon n, then mean PT can be reflected by some entropy in the initial stage. Then you would expect the initial stage calculation, which with epsilon n and E0 can be used to estimate the final, the Vn and the mean T correlation. And this has been confirmed within the Alice acceptance down to very low PT, that the final state calculations are consistent with the uncertainty with the final state calculation, with QGP evolution or with hydrodynamic evolution. This might not be the case with CMS or Atlas kinematics. So when you change the PT cut to a high PT, let's say 0.5 GeV in PT, you shouldn't directly use the initial state estimation to compare to the final state. You have to make sure you are using the final state hydrodynamic calculation to compare to Atlas or CMS connectors.
Is there an argument for this?
Or just run your models to see the difference.
I mean, there is of course the statement is that there is some PT cut where the initial state a predictor doesn't depend on PT. The hydro depends very sensitively on PT. Well, then there might be some PT cut where it matches, but
here, for example, if you want to, we have these assumptions, right? And the PT cut matters. If you reject the 40% of the tracks, this assumption might not matter. Or this estimation will not work very well.
In this plot here, where's the Alice plot?
I just wrote it for fun. So I will show you the Alice without. So this is basically without Alice point. I will show you I can my initial and final, and then the Trento, VHP hydro, and just scale and check.
Do you have a calculation for like Atlas PT cut that you show that they are different than initial state?
Have to be, because this, if they are different, initial state in this calculation, initial states are consistent with final state. When you do the final state calculation with different PT, they're different. Which means they will differ.
You check.
He's asking for that.
Yeah.
How much does it change?
I don't think I have the calculation, but they already make the prediction for Atlas. So if anyone send me the calculation, we can just program the prediction. But then here is Alice data point. So V2 PT correlation is positive for the present centrality 0 to 60%, and the results is rather flat with the centrality. And this weak centrality dependence better captured by up here Glasma calculation. And then in this calculation, I don't remember it's from Chen or from Bion, they are very kindly provide the calculation which is called the FSE final state effect only. So they find some way to reject the contribution from the initial momentum and a search space from CGC. So that when we see the difference, we see some differences, it might indicate the present of the CGC effect. But then within this calculation, you don't see anything so far. While if you compare IP Glasma to the rest, which are all based on Trento initial conditions, the results are very different.
So I also don't completely understand that the statement that the initial state predictor works. I mean, within like 0.1 or so. I mean, all of them are different, right? I mean, if I look at the blue dash line, it's not in the blue thing. If I look at the green thing, the slope is different, and the jetscape is so wide that I'm not able to say anything, and even then it doesn't go through. And then there's this dash line for directum, it's below. So for directum, it's below. For the USB hydro, it's above. That also you need to take into account. It's not a consistent shift that is different, right?
Sure.
So maybe with the 0.1 you can more or less agree, and then you're saying like, okay, with the 0.1 PT cut it matches exactly, with the 0.5 it doesn't. Well, I don't know. It has to be a little bit more precise, right?
Yeah, fair enough.
then you have to at least quantify exactly how well it does match with this cut, and with the other cut it might not match. But okay, here it also doesn't match. I don't know.
I agree. But then at that time when we were writing the paper, we would say, okay, so what the main differences between these calculations? Why IP plasma works slightly better or significantly better in peripheral collisions than all these triangle calculations? Is it because of the model itself or something else? Right? The similar for V3 PT correlation is always positive in data, which is also the case for IP plasma calculation. But if you look at the jet scale, it turns to negative for centrality above 10% for it, which is quite different from data.
The just game is they use many other data to constrain the model that can predict.
So they basically constrain also. So basically they have V2, they have V3, they have VPT, but they cannot predict the correlation between V3 and VPT. And this is a discussion which you mentioned that we should check consistency with different kinematic cut, PT, high PT cut, low PT cut, and also centrality determinations. Now we also have a 3D hydrodynamic calculation function. And it would be nice to also see if model can reproduce such effect when you are using centrality from forward and backward mobility, or centrality determination by mobility from middle mobility. Or if the centrality determined by either plus minus 2.5 in Atlas, or 0.8 in Alice. Those results are quite different. But then come back to the model calculation. So we were able to understand what's going on. And back in 2011, we had quite some discussion with Joanna. And then it turns out that the width of the nucleon matters a lot. And for most of these initial static calculations, we presented from Tradigen, this is from Jetscape. This is from VSP Hydro. I don't remember which one. And then there's IP plasma calculation. Oh, this is also Trento. Then you can see within the same model calculations, when you change the nucleon size, there's a dramatic change of the centrality dependence. If you even change the sign from positive to negative, if you have a very large nucleon size. This is also confirmed with IP plasma calculation, the final state calculations using different widths of the nucleon. And you can also see a very similar conclusion. But then my question is,
So the lab plot is initial state or
I think it's initial state estimation.
it's the initial.
Yeah. Based on trend, if I remember correctly. Clearly, we know there's a difference between Trento initial state model and also IP plasma. Those are different signals functions. Right? But then, my question is,
That's also much more subtle. I mean, people say this very easily if they don't work on IP plasma, but we run a lot of IP plasma events. It's almost impossible to reproduce the ATV scaling. In fact, it looks much more like Trento. So, I mean, if you ask people working on IP plasma, they would never say it's the ATV. I think like maybe it's very early times. Which is a good thing because the ATB has been ruled out already for 20 years. So, and IP plasma actually does quite well. There's a bit of subtlety there.
but yeah. So here comes my question. We also notice this nucleon width will matter a lot for the overall shape for PTV and correlation. So can we use the same parameters in the nucleon width and compare IP plasma versus Trento? Or you have different Trento, also different tune, Jetscape.
I mean, they don't even do the same things. They're not really comparable, right? The width that you put in IP glass will not do the same jobs necessarily that the W in Trento does.
Yes,
So
very good.
It's a little subtle.
That's exactly what I want to ask. Now we are starting talking about the data. How can we use the data to constrain the size of the nucleon? If the results using the same nucleon width give you different results in the final state from Trento and plasma, how can we constrain the parameter at all without model dependence? And should we report nucleon sizes in 0.5 Fermi with an IP plasma estimation, 0.6 from Trento? And how can we answer such information? That's actually what I want to discuss. I don't have the answer for that.
So one question is, you have only these width parameters. So what do you assume, a Gaussian shape of a nucleon, or how is the width related to some mass or charge radius?
I think this is based on what Saxon distribution. I also trying to.
Wait, the point you're asking about the nucleons?
That's right.
I think he was talking about the individual nucleons.
You get a nucleon width parameter, 0.4, 0.5 or something like that.
It's not a Gaussian?
It is a Gaussian.
It's a
Oh, it's a- oh, okay. Thank you.
It's a Gaussian width. There's some issue with square root of 2 of those. I think it's not, I think you shouldn't compare it to like a charge radius, because I think it's different by square root of 2 than the RMS or something. So, well, plus, I mean, yeah, the things that it does are not necessarily the same
But
as
then
like
still, the
charge radius.
is different by a factor of 2 or so. Yeah, you have 1.1 there.
Yeah.
With 1.1 in one of the calculation for just here.
Okay.
If I remember correctly, these W's are even larger than they seem. If you think of it as RMS width.
Yeah, you do multiply by square root of 2
Okay.
to 0.
So this is the way you define the parameter?
Yeah, it's just a parameter in a Gaussian.
Yeah.
I can't remember exactly. It's either has to do with 3D versus 2D or the RMS versus the.
It's whether you have a factor of 1 over 2 in the exponent, right, of the gas.
There is a 2 there in the definition. I can't remember why it comes in.
It's some kind of calculated root mean square in 2D, if you have 2D Gaussian or 3D Gaussian or something.
That's probably it.
Okay.
In Trento, it's just like a 2D Gaussian that gives the width 2 and then.
But this is the collision, and then we move to Xenon and see how can we probe nuclear structure with Xenon data. The uncertainty is very large for both data and also model calculations, and I don't know how precise we can say for this comparison. But we did one more step. So if we do the ratio between the rho in Xenon divided by lambda, we go to cancer sign effect. And similar work has been done by Atlas and check with different PD cards and with different centrality determinations. The results are more or less the same. So that we can basically use it to constrain the model directly. And this is just one simple calculation which they did before with different nuclear structure of Xenon with prolate and triaxial. And the Alice data really refer the description from the triaxial Xenon 49. But again, we have very limited data, 1 minute in total for the 8 hours of data taken. But it already shows quite some potential, I would say. And then in the future, we will have a dedicated proposal for the different collision systems. And we hope that with perhaps more than 1 day of data taken, we can do a lot for the structure at the edge. And one of the proposal has been approved is the oxygen collision at 1-3. And then in the beginning, we talk about with Saxon distribution, which is pretty simple. But then you also have more serious consideration with alpha class 1 structure, which Dean did quite some work with checking. But then we also have different consideration for the CGC, because when we really accelerate ions at the nearly speed of light, what could be the potential of CGC contribution? And when we think about this, so this is a very serious projection study based on the estimate the color glass condensate. There's a saturation with ion. So Alice collaboration prepared a dedicated document called public note for the projection study. Assume we have a 1 week of data taken, we will roughly have 5 to 600 mini events for xenon for oxygen. So this will be in the data points, and the values are guided by the adjustment calculations. But we scale to see what is the statistical uncertainty we will get in Alice. So you can see they are very precise for VM, V2, V3, V4, or normalized mandicuminant, or even the V2-4 with 3 sub-event method for identified particles, and the correlation between VM and VPT. The interesting part is particularly this one. This is also a calculation from, I think, Giuliano, Chun, and Bill. That if you only have the initial geometry contributions, you will see a decreasing trend for this V2 PT correlation. But if you have a CGC contribution, it's more or less flat. While you combine them with the 4IP plasma calculation, you get the blue. So this non-monotonic behavior will show you some indication for existence or appearance of the CGC contributions. But then,
Very brief.
but this No, not really. So here we are talking about D and D eta around 20-ish, 20 to 40, right?
That's very low.
That is, no, that's actually centrated to 40 to 60%. So it's not very perfect. We will have more than 100 million events for this region. And this is, so these points represent the real statistical uncertainty that we are going to have in Alice. So if you really have considering such a position, it would be easy to see. And there also with Alice kinematics, so if you a PT cut go to 0.2, we don't need a large eta separation to suppress the non-flow. While according to the latest calculation from Bill, the CGC is not a really long range effect. So if you apply large eta gap to suppress non-flow, you also remove your CGC conclusions. And Alice will be the ideal experiment to exclude most of the non-flow while still remain CGC conclusion. However, I have to emphasize for the overall serious considerations, there is no consideration at all about oxygen, the structure of oxygen 16, which is very serious. So all the results can be modified or will be modified if you have more a realistic consideration of oxygen 16 with alpha cluster structure. So for that, we also have more proposals from both Europe and the US. And this is a big proposal we submit to a new pack. It's a European nuclear research panel. And we want to see if this can be added into the long range plan. And a very similar program has been proposed in the US, but more with a bigger focus on Greek experience, I would say. But we also have, two examples with this here is we really want to explore the full potential of the LHC to see what can we contribute to the nuclear structure studies. One simple example would be calcium-40 and calcium-48. We study the neutron skin and also this very special structure for neon-20 because it's so obvious with all the shape that we would like to study. And then this is just an advertisement for the initial stage conference that we are going to organize in Copenhagen in June. And different from all the previous big international conference had in field, this is the only conference which had a dedicated section for nuclear structure. And we also want to welcome our friends from low energy to help us to have a more serious and precise initial stage calculation. Just show you why it is attractive. We will have a fantastic banquet with not charging much. Actually, all included in the conference fee. And receptions and IAC dinners and the boat trip in the Copenhagen tunnel are all included. And in particular, we want to welcome more students and young postdocs to join. And we will promise at least 50 and maybe above junior support. So living in Copenhagen normally is very expensive, but then we will make sure to cover the entire cost during the conference period for free.
What the reception? What is that room?
It's a university library.
Okay, the library.
So for our friends from US, the history of the library is actually longer than the history of US. Which is not surprising because the university is more than 500 years old. And let's bring to the end. And that's it.
Very naive question. I was wondering, can you have a sense about ultra excited states in nuclear? Clearly, it's only the ground state because the time scale is so that you were never excited before.
Because I think there are some calculations also by Zhou with our accelerator expert. They actually did some estimation. I think the lifetime they can stay with excited states like maybe traveling in several kilometers, while the LHC tunnel is 27 kilometers. So you don't need a lot of energy.
How easy is it to excite nuclei? I mean, there is some strong electromagnetic field for it.
Yes, but then that time scale would probably be.
Yeah, during the collision, there's.
Yeah, I was thinking about
No
can the
time.
collision first like a strong excitation of the nucleus before it actually.
The collision is very fast, but of course there is the what goes around in a millisecond, right? So that's not so fast.
Yeah, that's a different question. Can it excite when you're accelerating? and then-
Electromagnetically.
Yeah.
Yeah, that's not.
But,
And that's the right answer,
but it doesn't
Yes.
stay excited for a long time. Or?
It's only a few kilometers. I guess one of the estimation I heard is a few kilometers. Which is
Really? I would say that in excited states that they stay much longer excited.
Yeah, I was thinking more about, strong excitations that you have like a very broad state and then it's a very short lifetime and also by time reversal, you would be excited in a very short time scale.
Apparently the lifetime of the excitation only like microseconds.
Yeah, it would have to be something extremely broad.
So it would be nice to really see the concrete estimation or calculation. I only heard
If
like
it's only microseconds, then it's not.
so basically
These
what I
guys, they circle for hours in the tunnel. And the gamma factor is only 1,000, so it's not how much.
at least with this contribution, I want to say we really try our best to explore the 40 potential of Alice experiment. But Alice only took 1 million data events in total. And I believe that Siemens and Atlas can do so much better in this direction.
So why you only had 1 million?
We have a very slow TVC, as you know, we only take 10% of the data. Now it's much faster at 1 speed. The second question is whether we are prepared. So I think the answer is no. And remember that was the data taking was happened during initial stage 2017 when we were in Prague. And suddenly they say, oh, in the morning, oh, we will take the Xenon data. When? Why we have this idea? Oh, because it was some machine developments. We suddenly decided to have one day of a Xenon
It was
collection.
so random.
So none of us is prepared.
So I've got a question. In terms of, if you had to estimate the systematic error in the theoretical predictions beyond the initial state, but let's suppose we get the initial state perfectly, and then we connect to hydro. From hydro on, how much systematic error is there in comparison with experiment?
Very good question. I think for the existing base analysis, I guess just get the most precise consideration for systematics. But it's not
What do you
always the
mean?
case. Huh?
What do you mean? They didn't do a single systematic analysis.
What does that mean? What?
I'm not the person to judge. This is what I read in their paper with different consideration of systematics. Okay, I'm not saying you are doing a terrible job. What I know, because for example, I know some other analysis which didn't consider at all for their systematic uncertainty in the model parameters. It happened.
So what did Jetscape do for the systematic analysis?
We tried different
uncertainties.
data.
They tried.
That's the
Well,
biggest
that's-
difference. That's the biggest uncertainty in the simulations, right? How to map from fluid back to particle.
Well, they tried different data aspects. Okay, there are parameters that some of them. So what we do in Interactive, of course, for systematic uncertainty is to within our parameter range that we know, we take several of those values, then run like 10 or 20 of these at high statistics, and that then determines the systematic uncertainty. So we vary all the model parameters consistently with the Bayesian formula. And the delta F is only one example, right? We vary all the model parameters.
No, that we all do.
consistently.
We also do, but in the constraint phase, we even change different delta F and combine the posterior together.
Delta
So
F,
you will
yeah.
get the
So
different-
we just use the delta F that came out from the.
From the trend.
So, okay, yeah, that's not.
So what is the estimate? How much systematic error? You could say?
For about observing.
Let's say
It
Oh.
depends on the zone.
Yeah, you're talking about parameter or observable or?
observables. Let's say we measure these cumulants, these things. How much error is coming from beyond the initial stage?
Really depends on the observable.
You can get.
But a range, like
I'll see.
smallest to largest.
I mean, some very, very small. I mean, you can make ratios of things that like really isolate the initial state very well, and other things are like totally insensitive to the initial state and depend only on the final state. So
Again, if
it
you
really depends.
I think this actually nobody did, right? So we only vary all the parameters and not only the hydrodynamic parameters. So that's what we could do, of course, fix the initial state and then vary only that. And
Because
nobody did that.
from the structure side, it'd be good to know how much accuracy we need to satisfy the observables of interest.
Yeah, so the observable interests are the ones that we should look at. So the ones that haven't been done quite as precisely are like, yeah, like isobar ratios and things like, we know just from past experience that a lot of the final state systematics cancel out, but then again, we're starting to look at such precision that we need to know better than that. We need to know really precisely what is the uncertainty. That really hasn't been done yet in a systematic way.
For the small systems, I did quite a lot of systematically and varying like viscosity hydrodynamic things. So I'll show tomorrow like the oxygen and neon results. And
Okay.
that of course also more relevant for since those are the nuclear structures in computing. So
Yeah.
I'll show those things
Yeah.
tomorrow.
Because I mean, if we have good nuclear structure, neon and oxygen, there's not an isobar comparison, right, for oxygen. So we don't know how to.
Potentially neon
Oh, okay.
it is going to push a little bit more. It's actually not impossible.
Okay.
But I think that's the biggest question that we need to answer, is like with what precision
Okay.
can we really extract nuclear structure properties? And I don't know how precisely we have that answer yet. I think.
But my talk
We do
tomorrow will be
lower.
exactly on this question for oxygen and neon.
Okay. Very good.
And when you say nuclear structure information, you're interested in the formation parameters simply or more?
Whatever we can get at. I mean, so
Neutron scheme.
So neutron skin comes out of a comparison, say, of calcium 48 and calcium 40, or it comes out of calcium 48?
No, even just the isobar ratios, you are sensitive to this.
we can get much better precision if we can compare two different systems and make relative measurements. But
Well, there are not so many colliding speeds, right? So it's zirconium 96 and ruthenium 96, but lead 208 and oxygen 60. That's basically it.
Yeah, we only have very few.
yes,
And then
so far,
for the large ones, usually I think we get away very easily with just the deformation parameters. But for oxygen 16, I think we're really interested to have really the exactness of position. And then samples, of course, because we understand this is. I mean, yeah, we get these 6,000 or something like that probably from you, and then we put them in. We rotate them a little bit.
so whatever affects the geometric structure, especially at long scales, that's the kind of things that we can probe.
Yeah.
Including like fluctuations and correlations, not just like some average.
Well, from the neutron skin point of view, I think this zirconium ruthenium 96 might be something that is really interesting now because okay, lead 208, I think we're getting also quite precise, but I think for ruthenium, at least what we can I think get very accurately is the difference between ruthenium and zirconium. So if there's something you can compute there, yeah, because so many things cancel in this ratio, that the precision is much better than for lead 208. Even though I guess we know that 208 is more. It's easier to compute in some ways, much bigger.
Maybe this is for the afternoon, but do you really want to put in like distributions for all the individual nucleons from some sort of wave function?
Oh, yeah, so I was talking with Dean
Yeah.
about doing this properly with like some good section and then doing the Sledger determinant to have all the Pauli exclusions properly with the spin up and down and that.
Yeah, okay.
Something we don't do at the moment, but okay.
But I'm ending up is that the short distance structure of this thing you should never be sensitive to because it's something that would change.
So we are.
Well, it's,
we are definitely
Sort of short
sensitive to that.
difference behavior feeds it down somehow to a long
Yeah, but
distance
then from the
properties.
calculation, you know, you can always change the interaction, get all the observables the same, but the short distance wave function is very different because it's not an observable. So I wonder if you want to make the connection between the short distance stuff and the structure calculation, how do you account for this arbitrariness?
The observable question is always a subtle question, right? Because we really collapse the wave function. It's just like you have this pancake that goes through instantly. So of course, there's individual nuclear positions, they are not defined. I mean, there is a wave function. But,
Right, but
okay,
even
you
that
can
is, even
collapse
that is
it.
not uniquely defined at short distances, that's my point.
Yeah, there's a possibility that we are more sensitive to short range correlations than a lot of the observables that you are tuning your models to.
I'm gonna bring up a similar question when I talk next week, but this is always something that bothers me when you're at these high energy things and you want to get nuclear structure out of it, like up to which distances do you think you can get something?
But I mean, there's not extreme sensitivity to.
No, but in principle, it's an issue, and I wonder like what's the.
Yeah, but it's possible that one can, in post-processing, change that. Because what they want is a distribution of where all A nucleons are. You can go in and modify that. In fact, we were talking about doing that with the lattice calculations.
Right, but then you should be primarily sensitive to distances like rather than.
That's right.
For me, and then there's some residual dependence on what's going on the short distances, but that you can also change your cutoff.
Yeah, 0.2 Fermi, so that's
Yeah, I
rather
don't know,
shy. I
something
don't
of
think
that-
we're so
something of that
sensitive, like
order.
0.1, 0.2 Fermi.
Just taking a look on, like, definitely if you're probing something smaller than nuclear.
Yeah. Well, that's why we put this hardcore repulsion, so we have this minimum distance.
Yeah.
And we're definitely sensitive to that. Like if you change this parameter, then the MPT fluctuations will change. Because if you do a large dmin, then it spreads out more evenly. So I don't know if we know the dmin, because of course there are other parameters like the fluctuation parameter that also changes fluctuations. So there's a correlation between those parameters, but you cannot just put dmin to 0 and expect a good fit without changing the other parameters.
Yeah, so again, maybe it's going too far for this discussion, but I'm thinking about simulations like in short range correlations that measure at JLF or so, where you also have, the answer is you can change the operator consistent with your wave function, and then the physics is going to be the same and just interpretation changes. And I wonder if something similar is going on here, but then what's the operator? I mean, sure.
So whatever the energy density is when the nucleons hit each other.
That's just the scale, and then yeah, so you need to understand the scale dependence on it.
Maybe the positions of the nucleus are not observable. Okay, but the energy density operator, local energy density.
Yeah, there should be an operator that in principle runs with the scale. So, I mean, this is precision questions, I think.
Yep.
So this should be precision.
The short range correlation should depend on the scale. And we should
Yeah,
figure
the
out, we
way
should
you
figure out
interpret that,
exactly
the
what
way you
scale we're
interpret
probing.
that, right? So if you assume like just say this is my density, that you make an assumption what's the operator you're probing, but in principle to change the resolution scale of the calculation, the operator should be changed by unit of transformation.
So there's some sort of like gluon conversion operator that has two body currents and stuff.
Yeah, right. So, but there's like ways to go actually from the QCD
Yeah,
to this. And people have done this for that.
All right, so let's thank you again. Convene at 2, probably in that.